Man muss vorregeln. Ja, aber das ist ein Spiel noch Überlauf, dann kriegen wir auch genau, ja, die Sache ist natürlich Familie. Das sind deine Eltern. Dann will ich was Neues gemacht. Jedes Mal. Ja. Natürlich mein Aufwand. Ja, aber das doch halb übrigens sein. Wo man die Bevölkerung sieht, das ist genau, aber ja, durch den Stich. Ja, sure. In dem Sinne. Aber der no, the thing like that. No, that's the wrong one. Huh? These lights. It's the same remote. This is stupid. It's the same remote for three. So you put it. Get on. Ich habe mal die Vorlesung von gestern, wollt ihr den scannen? Ja, absolut.
Sollen wir starten oder?
Aber das ist mehr als komplizierter, weil man das Geld hat, den Impuls zu Good morning, everybody. I think very soon has this exponentially coming in the morning continues, we have a problem. And yeah, those who are hoping to escape the from speaking for both, to escape the potentials of Dana Anderson, Dana unfortunately went to the wrong place. So now he's in Hanya and he's in a taxi, wasting his pocket money on the long trip, lonely, swearing trip with a taxi. But he is helping the economy of Crete. He's helping. I hope he remembers to get a receipt. Yeah, that line. Actually, we should realize we should probably have said that basically because many people had doubt that they are now here, and some people, yeah, bad luck. So, Carrie gratefully took over to give the talk. There's one more slightly difficult issue, which is apparently the toilet down there exploded. So, but it's fine. But
The toilets.
Infrastructure in this village is in England, so it doesn't always function perfectly. So in the break, we can use the toilets of Nicastro for the 8-hour lunch. But obviously, if we all storm there during the break at the same moment, that will cause long queues. So if your flats are close by, then maybe you want to rush home and come back here during the break. It's good to walk. So, Carrie.
Cool. All right, very good. So I believe everything's being recorded. Everything's fine. We're all happy. Everybody's super awake. No hangovers. Cool. All right. So yeah, before I kind of get started with, I do think it's kind of, it's a bit unfortunate that, less than 50% of you are here, because I honestly think the lecture I'm going to give is the most fun one, but I mean, you'll be the judge of that. That said, before we get started, I wanted to show a few better drawings than what's over there, which I didn't erase so you can compare. And now you've got a lovely comparison for what happens when I make plots on a computer versus when I make them with my hands. But yeah, this is what the block bands look like. And this is what the block states look like. And so this is for a depth of 10 recoils and a depth of 20 recoils. And so what you can see is that at 10 recoils, indeed, all of the bands look like they're curved. The band gaps are increasingly vanishing. A whole bunch of people came and asked, they're like, do I think about this in terms of solid state physics? And yeah, absolutely you can. Like, I don't think there's, the analogy in some cases will only go so far because indeed atoms are not electrons, and I'm actually very glad of that because electrons are fast charged and very difficult to really handle. They kind of do whatever they want. Thankfully, some of what they want is like make light for us and make our phones work and these sorts of things. But in terms of being a cold atom control freak, atoms are a lot easier to control, in my opinion. And so, yeah, you can see that these flatter bands you can think of a lot more as valence bands, and actually these bands that appear like they just sort of, linearly increase in touch. In many ways, that's the limit of a free particle. And these band gaps will never truly go to zero, but they will become so vanishingly small that who cares? In fact, that's what they're going to look like. But indeed, for the deeper lattices, your lowest bands look more and more like harmonic oscillator states. Yeah, so that's what's going on here. These are just the plots. I thought it would be nice to show. So there you go. All right, onward. These are the Weidner states, again, just plots of them for two different lattice depths. So here we have 3 recoils and here we have 10 recoils. And indeed at 3 recoils, if you're describing your system in terms of Weidner states, you might want to take a step back and reevaluate your life choices. But I show them here mostly for the illustrative purpose of the fact that the tunneling parameter for an atom here to hop to a site here is governed by this overlap integral here, which is actually, this is quite appreciable. And you might say, well, that's just a tiny little bit. But then let's compare it to the 10 recoil case. Again, this is deep. This is still fairly deep in what we would call the superfluid regime. And I'll talk more about that in about 2 seconds. But what you can see here is that that overlap integral is rather small, right? It becomes vanishingly more and more small. And if I've got some time later, I'll put up some plots of what these various terms look like. So yeah, BECs and optical lattices. I say now in 3D, mostly because the maths, at least that I'm getting this from, is a lot more straightforward when one works within 3 dimensions. And if you want a reference for this, I think the best references for this, so that you don't have to rely completely on what I have to say, if you talk to anybody that does Bose-Hubbard model, and you go back to their PhD theses, this is really where this is going to come. Anna Maria Ray's thesis, as I mentioned, is another really nice resource for this. But this is the only time that I'm going to touch second quantization. Now, how many of you are familiar with the Gross-Pitaevsky equation? Okay, a few of you. This is definitely one thing that I don't want to spend a whole lot of time on. But the Gross-Pitaevsky equation is a way of describing, it's an approximation, but it's a way of describing atoms in a BEC. And so what's going on here, if I use, we'll go green, that way you know. If you have a Hamiltonian for, we'll call it GPE, Gross-Pitaevsky equation. Basically, it's going to look like p squared over 2m plus whatever external potential you have, plus something that takes the form g mag psi squared. And the form of g is well written out in many cases. This involves things that you hear a lot of atomic physicists talk about, like scattering lengths, et cetera. The mass of the atom is in there somewhere. There's probably some h bars, you know. I don't know that I write it out on these slides, but I might. Let's see. Okay, nope, okay. But, and if you're really curious, let me know. I do have it written out. I just don't want to dig it out because of the interest of time. This is not a lecture on the GPE. And this is fairly well accepted as what's called the mean field treatment of BEC. There are treatments that go beyond this Gross-Pitaevsky equation. This is very, in many ways, a simplification, but a good simplification that has its merits when considered empirically. And, you know, but also theoretically. The point of the GPE is that it's got this nonlinear term. And this is basically, if you've got an atom and it's surrounded by a BEC, all it's really doing is it's saying, well, you know, all of these atoms, we're going to average over everything that's in this, you know, big green blob. And then we're going to say that the interactions on this atom are going to be proportional to the sort of amount of big green blob that's around the atom. So an atom over here will feel less of this nonlinear interaction than an atom over here, because basically this guy here is mag psi squared. And it's nonlinear, so that makes everybody happy, which it really doesn't. And the fact that it's nonlinear should alert you to the fact that it is a bit of a, you know, it is an approximation. But what we'll actually do then is we'll go into second quantization here. And I promise you that if you don't quite get the next couple of slides, it's all good. Then we'll go into story time. If you do get the next couple of slides, all good. But what you see here, that's p squared in 3D. That's your potential, again, in 3D. I've basically promoted all of my x's to vectors. And then here's this nonlinear term. And I'm integrating everything over x for a reason. That should become clear. Wolf Dana's calling, but I can't exactly hear. Do you want me to hear? Legit, just answer that.
I could put him on loudspeaker.
No, I don't really want to. I feel like there would be some way that he would have me lose my job. But yeah, so basically what I've done is I've promoted, all of these things to operators, but then also my state now is an operator, and that's what's going on. This is sort of the second quantization. And so what this term is describing here are collisions. This is sort of the interaction of the atoms with themselves. And what you can then do is you can say, okay, the whole goal of what's going on here, to try to get this so-called Bose-Hubbard Hamiltonian, which allows you to describe the basically what goes on with very cold bosons in deep optical lattices, is you say, okay, I've got a deep optical lattice. I will assume that my states are Wannier states. So that's my Wannier state. And you see that there's a W0 here. And so what I've basically got here, I feel like this should be the creation operator, not the annihilation operator. But basically what we're doing is, and I definitely think that's a typo, is that we have the lowest Wannier state, and we have a creation operator at some lattice site J, like I had yesterday. And then this W0, this is the lowest band. So the whole point of describing BECs in optical lattices and why BECs are such fun tools for optical lattices is that they're really, really easy on a relative scale to just put them into the ground band of the lattice. And the reason why is because they're cold. So as long as you're not too violent with them, they behave. That's my experimentalist thing. So what you can actually do is you can plug this in and you can do these integrals and you end up with something that looks like this after shoving factors into these two terms. And let me see what I've got. So basically this guy here is the tunneling matrix element. This is really the chance for an atom to jump from site to site. And we'll call it J. And it's typically called J in these types of things, although sometimes you look at papers and they give it some other weird letter. And this is related to the overlap of the states that I've drawn for you. I guess they're over here. And so that's kind of the motivation there. And the on-site interaction and energy, if you ignore the fact that the University of Bristol has the need to put its website everywhere, probably shouldn't say that on YouTube, this is related to this collisional term. So this on-site interaction energy, this is basically the energy penalty that you pay if you have multiple atoms on a lattice site. Yes?
I don't really understand why are you limiting to being in the lowest line bands? Because if you consider just like you have atoms in a lattice potential, the two only thing that you can do is interact with each other inside your potential. Let's say so you forget all like the next neighbor, whatever interaction, and you can hop from one side to the other.
Yep.
Even if you're in a higher excited state of your lattice, that's still the only two things that you can do.
Yeah, but the way these terms are going to manifest themselves are going to be a lot different, right? So I mean, in many ways, the simplest answer is that it's simple, and this is how we can recover the Hamiltonian that I'm getting after. But I mean, for example, if we're summing over all the lattice sites here to make this psi. What if we also have to sum over bands, right? That's going to turn these expressions into the technical term is a giant nightmare. And there are higher band approximations. Like there are people that have, gone boldly where, most of us kind of shy away from and do these higher band approximations. But the lowest band approximation is basically all it's saying is that we'll get this lovely little Hamiltonian with all of these nice well-behaved terms as long as things are cold. But you are, in many ways, correct. However, if you have high enough bands, your atoms aren't really confined by the lattice anymore. And then they're not, and then this whole idea of, nearest neighbor interactions becomes a bit waffly. Yes?
Why is the tunneling matrix element not depending on JJ prime? Is it some kind of approximation going in there that you say they need to be neighboring sites?
JJ prime, yeah, no, they have to be neighboring.
Okay.
Yeah, I mean, you can calculate this integral for sites that are non-neighboring. It's going to be, that's another clever way of writing zero.
Some approximation, say, they model that is going to zero for whatever, two sites.
Yeah. It is an approximation, but it is a really good one. But yeah. Cool. Excellent. So how then do we describe BEC in an optical lattice? And this is kind of getting into the two ways of describing atoms in an optical lattice. This I include mostly because, well, it's fun. But you can play in these two different regimes and it's good fun. So basically describing BEC in an optical lattice, this depends a lot on the lattice depth. And in many ways, it's the ratio of U over J. It's the ratio of the on-site interaction energy to the tunneling energy. And the tunneling and the tunneling probability, this J, it drops off basically exponentially with the depth. And so J gets really small really fast. So if we consider M lattice sites within bosons for big M and big N, if our U over J is much, much less than 1, basically, if our tunneling parameter or our on-site interaction energy parameter is quite low, you end up with a superfluid state. And so this is a picture, this comes straight out of Marcus Greiner's thesis. If you, like, this is where I learned, this PhD thesis is where I learned lattices. And I believe he covers all of this as well. And so what you can see is basically this little cartoon of there's multiple atoms per lattice site because the energy penalty that you pay isn't that large. And it's actually quite easy to move between sites. And you end up with these lovely quantized momenta that I was talking about. And I'll show hopefully a few more pictures of this. But this is just a really nice clean one where you can see the 0 h bar k state, 2 h bar k in x, 2 h bar k in y. These cross terms arise because you do indeed have multiple dimensions here, whereas everything I talked about yesterday was in 1D. But you get a superfluid state that's just a multiplication for each of the atoms that you have of a block state in the lowest band, which is cool. And you can, in many ways, you can select your quasi-momentum. Some people came and asked me about like the width of the state, right? Because a BEC isn't a delta function. Nature, see, I can't even draw delta functions. Nature hates them so much, right? A BEC has some width, delta P. And we try really hard, right? This is the, what did we call it? Delta kick collimation is the, this matter wave lensing, all these types of things. Researchers try really hard to keep these atoms nice and collimated and well behaved. But you're never going to quite get a delta function because then that's assuming infinite energy. And indeed, that's not something that we have. And also when you start talking about the swap plus C of the thing that you're going to build and how it's going to revolutionize the world, yeah, infinite energy doesn't go well into that. So that's a joke for my industry people. Like nobody laughs. Very good. It is early. So basically that's all it's saying. And so in many ways you can select Q. It's fairly straightforward to actually make a BEC loaded into a lattice and have it have 0 quasi-momentum. But you will always have a little bit of a width there. And the degree of to which that ruins your day is really up to what you're doing and how well you're controlling things. In the other limit, basically where J becomes very, very, very small, right? It drops off exponentially. And our on-site interaction parameter, this energy penalty that we pay, becomes very large. You end up with the so-called Mott insulating state, where basically your Mott insulating state is that at every lattice site, you just create a particle that's in the ground Wannier state, which I'm calling here 0 because I like labeling Wannier states with Fock labels. And if you listen to my talk on Monday, you'll understand why. And so the Mott insulating state looks something like this, right? This is the eggs in an egg carton, and this up here is the broken eggs in an egg carton regime. And indeed, experimentally, you get a blob. Yay, physics blob. We love physics blobs. And then this happens, usually this transition happens at around what we call 5.8 times Z, where Z's the number of nearest neighbor interactions. I apologize to my fellow Americans in the audience. When you teach in the UK, you start calling Z Z really, really quickly. Because otherwise they're just very confused. But yeah, so this is basically the number of nearest neighbors. So, in 1D, Z would be 2, in 2D, it would be 4, and 3, you can extrapolate. Start telling me about 4D lattices and my head just kind of explodes. Cool. All right, so basically we've got the Bose-Hubbard Hamiltonian, which takes this form. This bit here is the nearest neighbor bit. Basically, usually when you see these angled brackets, that's implying nearest neighbor interactions. But if whatever you're reading doesn't clarify that that's actually the case, then whatever you're reading probably should have. And so shallow lattices, basically the atoms are best described by block wave functions. The critical bit is that they're localized in momentum and delocalized in position. So you get these lovely delta-ish functions in momentum space because quantized in units of 2h bar k, but in position, this is the broken eggs in an egg carton regime. And the atoms in a deep lattice basically are best described with Wannier functions. They will be localized in position where they know exactly where they are, but once you drop them and you start taking pictures of them in time of flight and you're asking them for their momentum distribution, basically they're like, and you get a lovely little blob. Cool. All right, so this is where I'll go to the outline of the things I'm going to talk about today, because everything in the past 20 minutes was stuff I was going to talk about yesterday. So this is what I would really like to call the fun bit. I really enjoy giving this talk. Very quickly, I'm going to give the optimal, this is where we're going to talk about optimal control. And this is one of these where if you never touch BEC, you never touch a laser, you don't even really do physics, you can probably use some optimal control. Or you can't. Honestly, I've had conversations with folks where they're like, I do shortcuts to adiabaticity. And I'm like, that's smarter than optimal control. Keep doing that. Am I right? So that's where that's at. I will, though, however, tell you kind of the, I'm going to skip this bit, but I will give you a dictionary of quantum optimal control so you can understand the types of, the types of jargon that you see. And the point of this isn't necessarily so you understand what I'm going to say, but when you understand what people say when you start reading papers about this sort of thing. And then what I'm going to do, yes.
We'll have a little hands-on competition on optimal control theory later.
Will we? Cool.
Yeah.
Not by me.
Came out of a Raki Loden dinner conversation.
Oh yeah. Oh no. That's right. That's right. I know exactly what you're talking about. Yes, we will have that. Yes. Yeah. It turns out Rocky fueled conversations can be useful. You just wake up kind of thirsty in the morning. Yeah. So, and then what I'm going to do, and this is really where the fun bit is I'm going to tell you about my PhD work. And this might seem really self-indulgent. And I mean, to an extent, it kind of is, right? But I'm going to tell you what I did. And this will be a bit of a warm-up for the talk that I'll give on Monday if you're going to Hania. But it's also, I'm going to tell it to you in sort of these are all the things I did wrong. And hopefully that's useful. So I'll tell you a little bit about, what, I'm going to really gloss over what atom interferometry is. And I'm going to focus a lot on practical quantum control. You want to learn about atom interferometry? Well, Inno gave a couple of very, very nice talks. Alexander's continuing to talk about this. Jason Hogan knows more about this than 6 of me put together would. And so let's just dive right in so that I'm done on time. Sound good? So, dictionary quantum control. These are all of the terms, and you'll get some lecture notes from me. So, if it's just proving too much for you to stay conscious right now, I understand. And, well, you'll get this later. So, quantum control. Very well named. Control of quantum systems. All right, done. Good. Moving on. There are 2 types of quantum control. And I will really focus on the optimal control. But there are a lot of people, especially kind of when this was starting to become a field, that made their living off of coherent control, which was basically you had a model for your system and you knew where you wanted to go with it. And you kind of knew where you started and where you wanted to go. And you set your system up. This is a very path integral like idea, right? Where the idea of the whole path integral is that the particle can take all paths, and then the one that constructively interferes is the one it actually does. I mean, that's exactly what's going on with a lot of coherent control, right? It's making use of the interference between all of the possible paths and designing things such that the path that you want to take that goes from point A to point B is the one that's the most physically favorable. This is often called the physics first approach, and it works if you've got a good model of your system. A lot of what got me into quantum control in the first place is actually, kind of the step one of what I tell you not to do, which is that I understood the physics of my system, but I didn't understand it deeply enough to really design things well. And so that's why I jumped straight into optimal control, where you optimize a process and then afterwards you're able to extract physical insights. So this is very much the control first approach. And it works. But sometimes it works and you get something out and it says, oh, you want to go from point A to point B, you should take this huge looping path. And and you're like, why? You just made me climb 6 mountains. And trying to understand why this optimal control algorithm is telling you where to go and why it's telling you to go where you should be going, that's a bit of a struggle, honestly. So you can control state transfer. This is very much what I was talking about, where you start in one state, which I'll call psi A, and you'll go to another state, psi B. If you're one of those people that likes to work with open quantum systems, you can write this whole formalism in density matrices. I'm skipping that because it is mathematically more involved. I do have some notes on that if you're interested. For an experimentalist, I like open quantum systems a bit too much. They're just fun. And so, yeah, we're going to work in closed system space where everything evolves unitarily and nothing ever dissipates and your lasers never come unlocked and they definitely never break. You can also optimize unitary operations. So, yes. It is. It is. Yes. Yes. Or Nirvana, depending on. Yeah. Yeah. Hovering above your optical table, watching it as everything works. Yeah. Brief interlude story is I got my experiment once when I was in Boulder and I was doing my PhD. I was doing the experiments that I'm going to tell you about, and I got it just working really, really nicely. And I was working with like a first year grad student at the time, and he was like, cool, well, I mean, I guess, you can go home and everything will be good tomorrow. Did you say no? Yeah, this guy knows. The fact that you came back to sit in the front row again gives me confidence after all of the crowd work. But yeah. But no, that's exactly right. So he was like, cool, you'll just go home and it'll work tomorrow. I was like, nah, I'm working with this until I can't see straight. And he was like, why? I was like, because it's working. I might come in tomorrow and the laser will just have decided to spontaneously combust. And he was just like, he didn't understand. And then like finally he came back to me a couple of weeks later and he was like, when I was kind of getting on your case about staying late when the experiment was working well. And I was like, yeah. He's like, I get it now. So when it works, run with it. Run with it. It will save you so much time, even if you're like, oh, but I have so many things on. Like, you'll have so many more things on in the future if you just run with it while it works. Run with it while it works. I mean, none of this is worth killing yourself for. Like, physics is fun, but, have other things in your life that you enjoy. But when the experiment's working, don't have anything else in your life that you enjoy. Good. Okay. So yeah, unitary operations, this is very much like gate optimization. I'm not going to talk a lot about it because thankfully this isn't a quantum computing conference. Sorry. But yeah, you can do that. And actually unitary operations are quite nice from an atom interferometry point of view, right? Say you want to optimize a mirror that, and you want it to just implement this unitary, or you want it to implement a phase shift, or you want it to do something like that. That's very much where unitary operations can help you, because it is more difficult because the dimensionality of your system is higher, right? Because instead of optimizing a vector that's a state, you're optimizing a matrix that's now n squared in the number of elements. But yeah, it does work and it's good fun. I will talk primarily about state transfer. Again, I've got a few notes, not all that much on unitary operations, but I can talk you through how one would do that. You can, and when I talk about choosing between two loops, anybody that has an actual like electrical engineering control background, please just close your ears for a second. Because when I talk to my electrical engineering, like actual control people, they hate this. Because to them, open loop and closed loop control, basically, this is one of the times that physicists took terms that meant something that was perfectly reasonable and made it then reappropriated those terms to something else that meant something that was perfectly reasonable. But these two perfectly reasonable things are at odds with each other. The way I'm going to describe open loop control is that you're optimizing a model. This is a very like experimentalist biased way of looking at it. It's not the lack of feedback. It's just that you're optimizing a model. Closed loop control, which for the control people means there's feedback, I'm going to use it to mean that you're optimizing an experimental system. And the idea then is actually that the experiment is what's providing you with real feedback. And so again, this is a very experimentalist biased way of looking at things because indeed, it's taking the view that if you're not actually optimizing an experiment, what are you doing? And you can optimize, we'll talk a little bit about this. You can make it so that you're like, okay, I want my control to be fast. And, I want it to be good. I want it to do what I'm telling it to do, but I want it to be fast. I don't care that much about energy. Or you can say, actually, I want it to not expend as much energy. Or I want it to be really sensitive to changes in parameters. Or the exact opposite. I want it to be very robust with respect to changes in parameters. We'll talk a bit about that tomorrow. I'm going to have to go away and like sit and stare at the mountains and think about exactly how I'm going to tell that to you tomorrow. But that's my problem, not yours, or it will be your problem tomorrow. Yeah, you can optimize these controls. So let's talk a little bit about how this works. So state transfer is fairly straightforward. You've got an initial state, which I'll call psi naught. You've got a desired state, psi d, and you've got a Hamiltonian that's time dependent. Doesn't necessarily have to be, but it usually is. And you've got some controls. This could be as simple as I have a knob that controls my laser power, controls my lattice depth. This could be as simple as having a knob that controls your magnetic field. Usually what these knobs are in a real experiment is some form of electromagnetic field. Very rarely is it something else. You may be optimizing transport, in which case you might be optimizing, say, the position of your magnetic field coils, or the phase difference between two lattice potentials that you're using to make a running wave that you're using to transport atoms. You could be, this is related to the rocky-fueled conversation. But basically what we've got here is that you have an initial state, a desired state, and then some knobs you can turn. And those knobs that you can turn have to be in your Hamiltonian, otherwise it's not going to do anything. And you've got some time t. You can vary time, but it's just easier, especially if you've never seen quantum control before, to just say that you have some fixed time t that you want to do this in. And actually, in practice, what you'll do is you'll either leave time as an optimizable parameter, which works, that's a thing you can do, or you sort of optimize for different values of big T, and you see how well things do, and how well you actually achieve this desired state will typically get better and better as you increase your time. Cool. So your final state after some evolution, where basically you've just done unitary evolution, you've got your lovely time-ordered exponential, and you're either doing this in your experiment, in which case you don't have to think about the maths behind it, or at least not when you're running the experiment. You're usually thinking about, is the laser actually doing what I want it to be? Or you can do this computationally. If you do it computationally, I think everybody, theorist or experimentalist, should learn one fun way to solve the Schrodinger equation. And so I recommend it. Look up the split step method. It's the simplest way to start. And usually, not always, and actually I'm going to give you a case in a second, your Hamiltonian actually turns into something where you have a bare Hamiltonian, and then you've got another term where your control multiplies your Hamiltonian. If you were amplitude modulating an optical lattice, this would be exactly what's going on, because this h sub n would be your cosine term for your potential, and your u of n would be some term that sort of says that you're scaling the depth of your lattice up or down, right? But this doesn't always have to be the case. It's just very often the case. And most of the time when theorists work on control problems, they use control problems of this form because it does make the maths easier. You don't have to do any chain rules. Cool. So I'll tell you a little bit more kind of dictionary-wise about landscapes and algorithms. Good, I've got plenty of time. This is nice. So an optimization landscape is defined by the set of optimization parameters. So this could be, the power in a laser, the gradient of a magnetic field, the position of a set of coils, or something along these lines. And there could be many, many of these, right? You could have 6 lasers where you're controlling their power. And those 6 lasers will define a 6-dimensional landscape. And so that landscape is basically, the mountainous region, right? This is often what's called, if you're trying to maximize the overlap between 2 states so that there's, your final state and your desired state are as close as possible. You can think about it as being a mountain range, right? Like the mountains around us. One of the things is that, you don't necessarily know. Kind of the analogy that's given is climbing around a bunch of mountains in the fog, where if you plot me somewhere, if you made it very foggy and then you plot me somewhere in the hills around here, I could really easily tell you which way is up, right? Because I'd start moving and I'd be like, well, I'm either going uphill, I'm going downhill, or I'm not, right? And I would be able to sort of take my own little derivative. And this is related to the gradient-based optimization that the machine learning folks were talking about 2 days ago. But what I couldn't do is when I get to the top of the mountain, tell you if it's the tallest mountain. Because it's foggy, right? I can hardly see in front of my face. So that's kind of what you got here. You can have various different types of landscapes. So basically, this would be the case of having a whole bunch of really suboptimal solutions, and then one really, really nice solution up here. So basically, if we want to get to the kind of the white caps, the yellow white caps of these mountains, that's a good solution. You can have just a few mountains in your landscape. And these are sometimes called attractors. So if people are talking about attractors, they're just talking about if you have kind of a gradient-based algorithm, which is you walk, your little algorithm climbing up the nearest mountain, the mountain it climbs is an attractor. Okay, cool. That was one of those terms where I was like, what does this mean? And it's definitely got, that's all it means in the context of optimal control. You can have a nice smooth landscape, right? Where basically, you climb to the top of one mountain, you descend a little bit into the valley, and then, oh, look, there's another mountain, that's nice. Or you can have a very rugged landscape where basically each of these good solutions is something along the lines of you got to go up and all the way down, and up and all the way down. It's like climbing around the hills of Bristol. And so basically, this is, what you're doing effectively is your initial guess is plopping you somewhere in this landscape, and there are various ways that you can try to find your way to the top of a mountain. Now, I'm using the terminology of maximizing something. It's actually just as easy and very commonly done that what we do is we flip all this stuff upside down, and then we talk about minimization. And so it's kind of, and this is actually really nice to do for a few reasons. One is that it's nice to get something close to 0. It also makes your plotting nicer, because if you're plotting something on a logarithmic scale that's close to 1, basically you really care now at the difference between 1 and 0.999 and 0.99 and 0.9, right? And so it actually, when you're now looking at 0 versus 0.0001 and 001, it becomes a lot easier to see and to visualize. And so often when I'm optimizing, I'm rarely maximizing. And if I'm ever maximizing, it means I'm using code or a model that somebody else wrote, because I don't write maximization problems. I write minimization problems. It is said that if you have no constraints, if you can put infinite laser power into your system, infinite magnetic fields, infinite whatever, that you have no local maximum. And this is something that Herschel Rabbit said back in 2004. no offense to anybody, this is kind of a useless statement from an experimental point of view. I will never have infinite laser power. Ergo, my optimization landscape will always be constrained, right? I might be able to turn my laser up quite high, but if I can only get 1 watt out of my system and my optimization, my control says, oh, I'd really like 1.2 watts. Like, yeah, me too. Tough. And so in many ways, you always have constraints. And when you have constraints, you have what are called traps. And so traps are basically, like I said, these suboptimal solutions. So good. Now, there are a few types of algorithms. If I've got some time, I might talk you through some of these algorithms. That said, there are just tons and tons of algorithms. They come into 2 types. There are local and global. Oops, wrong way. I wanted to hide that. There are local and global algorithms. A local optimizer is very much like this gradient descent that we talked about, where it just climbs up the nearest hill, gets to the top and goes, hooray! And it might be up here, but it also might be down here. And if it's down here, well, that's not the hill that we want to find. And if it's up here, awesome. And so in many ways, if you're using a gradient-based algorithm, you usually want to guess a whole bunch of times and try to span your landscape as best you can, which gets really, really hard really, really quickly, because if you've got a huge dimensional space, or rather in a huge dimensional space, it gets very, very difficult very quickly, because it's very difficult to sort of sample and span a very large dimensional space. That becomes computationally expensive very, very quickly. And so in many ways, this is called exploiting. You hear people talk about explore, exploit. This is very much the exploit. And so what you actually want to do is drop a bunch of little initial guesses and hope that you hit every single one of these mountains, so that a whole bunch of them are going to be really, really crappy, and this one's going to be good. And what I often tell my collaborators, I work with a bunch of collaborators in robust control, and they're very, very theoretically minded. And they really want to know, they want to analyze all of the controls that they get, even these ones. And I repeatedly tell them, I couldn't care less about those, right? If you're looking for an optimization, say that this yellowish white up here represents a unit sort of overlap between my desired state and my final state, and this represents down here 30%, I don't care about the 30% overlap. That's completely useless to me. But if we want to analyze this amazing solution to death, I'm on board. Let's do it. And so that's really what's going on. You can also have global optimizers. These are sort of, so your local optimizers, these are your gradient-based algorithms. There are a bunch of them. Grape is one that was developed for NMR, and people use it all the time. Grape is fantastic. There's other ways, there's stochastic gradient descent, all these sorts of things. If people start talking about LBFGS, that's more or less what's going on. And then these global ones are often, these are your genetic algorithms. These are your sort of like particle swarm optimizers, these types of things. And basically what they do is there's generally, gradient-based optimizers are deterministic. If you plop your seed with the same sort of parameters for how big steps it takes, all of this stuff, it's going to find the top every time. But these global optimizers typically have an element of randomness in them. And what you can do is you can do something along the lines of simulated annealing, where you turn down that randomness as a function of time, and then the thing will start exploring. And that's sort of what this global optimization does. And then you sort of turn down the explore parameter, and then they tend to focus on, the thing that actually matters. And so this, these populations that are sitting there spanning this landscape will all kind of converge on the good solution as you turn down their ability to really explore. And this is really, really commonly done. But these global optimizers are really, really nice for just seeing what you can see. But they're not always the most efficient. Gradient-based optimizers are often really quick. But these global optimizers, because there's this inherent randomness, you can run it 10 times and get 10 different solutions. If you run it 10 times and you get 10 of the same solution, you probably didn't shuffle your random number generator seed. Ask me how I know. But and so there are this sort of explore in the global sense versus exploit in the local sense. This is really important. There's a reason why I've spent the past 5 minutes talking about it. And you can couple these. I have a project going on right now. There's some really, really cool work out of Irene D'Amico's group in York. And out of Irene D'Amico's group in York, where they wrote this awesome genetic algorithm to optimize these like spin networks. And they did this really cool work. Where they were able to show they could have this 5x5 grid of spins that they were coupling, and they could go from, the spin down here to the spin up here. And they used this genetic algorithm to find it. And they wrote it in Fortran, which means that I have to now learn how to write code in Fortran. We basically took that and we said, cool, let's optimize let's use the global optimizer for a few iterations, take the best solutions, and then use the local optimizer. These sort of coupled, global local optimizers are becoming increasingly popular, and they're really, really fun. So cool. You can also so you can describe an algorithm's ability to explore versus exploit, and you can tune how much one can explore and exploit. Cool. So, yes, this is actually a very important point. A gradient-based method requires you to know a gradient, and you have to calculate derivatives. If you're working, computationally, that's fairly straightforward to do. You sit there, you calculate numerical derivatives, and everybody's happy. If you're working experimentally and you have to calculate these derivatives, that becomes pain and suffering very, very quickly, especially if your experiment isn't particularly stable. And so you're sitting there and you're like, okay, experimentally, I'm in a 6-dimensional space. I want to take a 2-point derivative. That means I have to do, 12 experimental runs to calculate my gradient. And because I'm doing a 2-point derivative, my gradient approximation is actually not that great anyway. And so, these gradient-based methods, they work really well, but they work very, very well in simulation where you've got models. And in experiment, you've got to be clever, and your experiment should probably be fast and stable. So cool, go, go, go. Oh, that's the laser button. Okay, that's the not laser button. Now, when you optimize, you have to tell this thing what you want, right? So the computer, and in the experimental control, right, it doesn't know. So you have to decompose your problem, this entire problem. This is kind of the crux of why optimal control theory is, and optimal control practice, I should call it. Theory is a very strong word for what I do. You have to decompose this thing into one number that you need to minimize or maximize. And anybody that's ever looked at their H-index knows that it's extremely difficult to decompose something as complex as one's academic journey into one number, right? It's very, very complex to decompose one's entire physical model, one's entire experimental system into one number. So you've got to be clever about it. And you also have to understand that by kind of doing this, single scalar that, you make number go up good, make number go down bad, it has intrinsic flaws in it. And so, you just have to be careful. Oftentimes, if you've got something that works, you just run with it. And that's why sometimes when you look at papers, you see these like functionals that are just completely nonsensical. And the reason is that the PhD student played with them ad nauseum, found something that worked, and never fixed it. Fine. Try to avoid nonlinearities in how you sort of define your fitness, but sometimes it's inevitable. So here's an example. Look at this big, long equation. This is for a control, U, a final state that I call psi at big T, and a desired state psi of D. And so my example functional, this is now J, the functional, not J, the tunneling parameter. My apologies for using the same term for this. It breaks it down into 4 bits. And so what are these 4 bits? So you can have as many terms as you like, but more terms is more complex. Basically, this here is what we'll call an error or an infidelity. This term here, where I've got the overlap, the squared overlap between these 2 terms, that's known as a fidelity. You'll often see it written as F or curly F or whatever. That's the fidelity. Usually if I'm minimizing, which is what I like to do, I take 1 minus f. So that's like a fidelity error. Sometimes you'll see control people, they hate that we square this, right? Because that's nonlinear. Like real control people hate nonlinearity. And if you've ever, tuned a PID controller, I think you'd understand why. Especially one that drives AOMs, because that has an intrinsic nonlinearity in it that you can't get rid of, and it's pain. So what you have here basically is a fidelity error. And all of these lambdas are just scaling factors that tell this number how important each of these little bits are. This term here for our control is just trying to minimize energy. So if I take the square of my control, that's going to be proportional to the energy that I have to put into the system to do whatever it is that I'm trying to do. So if I'm minimizing this term, and I can kind of put an envelope on it, these lambdas can be time dependent, they don't have to be. I can just say, if I make lambda not small with respect to lambda a, and I make lambda a constant just to make it easy, then I'm actually not going to care so much about fidelity, but I'll care quite a bit about the energy of my that I'm putting into my system, right? So basically what I've got is something where I say, okay, I actually just want to put as little energy as possible into this. Or I can say, I actually want my control to be very smooth. So I'll penalize for the derivative, because a high derivative means that this thing changes like absolute madness, right? And so if I want to minimize this derivative, I'm minimizing changes. This is also known as a regularization term, and you'll actually often find people that just kind of do this by taking a Fourier transform and cutting out high bandwidth parts of their control and things like that. You can also just take a derivative and integrate over it, and you'll achieve a lot of the same thing. And then this here, I won't talk a whole lot about it, but you can actually penalize for being in states that you don't want to be in over the course of your optimization. Say you have a 4-level system and you want to go from level 1 to level 3, but if you end up in level 4, the atoms will just go and you'll lose them completely, right? So then what you can actually do is you can say, well, listen, over the course of my optimization, I need to keep my population at a level 4. That's what terms like this will do. And there's a lot of really cool work on doing optimal control in these so-called like restricted subspaces. Christiane Koch in Berlin has done a bit of work on that. So cool. So your weights will determine the relative importance, and you can actually optimize multiple state-to-state transfers. It gets complicated, it gets expensive computationally, it is very difficult to have that converge. It can be actually quite impossible to converge if you're not treating your physics correctly. But what you can do is you can just have sort of a J equals a J1 plus J2, where J1 is going from one state. You can't optimize one state into 2 states at the same time, but you can optimize sort of an initial state 1 and initial state 2 into a final state. So you'll want to sum multiple fidelity terms. This one picks a final time. You can keep that as a free parameter. And indeed, the fastest possible transfer that you can get defines a quantum speed limit. I don't actually really like quantum speed limits all that much because they're really difficult to prove rigorously. It's also really, really hard to say if what you're doing, the control that you found is the optimum control. It's very hard to know when you've hit your global optimum. So usually what you want to do is define good enough and stick with it. Cool. So I'll just talk a little bit about functionals for unitary optimization. What you can actually do is you can define something very similar to your fidelity, but it's just between your final unitary and your desired unitary. You'll basically take the trace, divide by the dimensionality, so you get something that's bounded between 0 and 1. And this is basically the equivalent of a fidelity for a unitary optimization. Cool. So this is really the fun bit. But what you'll want to do, and I'll take you through a case study, an example. But what you want to do is define your problem. What type of problem is it? Open, closed, state transfer, unitary? What are you doing? And you can determine what your controls are. What are the knobs that you can turn? How do they affect your system? What are the limits that they have? and if you're working theoretically, talk to your experimentalist friends to figure out what's feasible. Because if you come to them with a control and they're like, I can't turn that laser up that high, well, then you're back to square one. Understand what you can measure. What information can you get out of your system? For a lot of the optimization that I will do sometimes, I will, especially experimentally, I can't extract phase information readily. Sometimes you can. Understand that phase can sometimes be very difficult to get out of the system. Amplitudes, not so much. Sometimes it's the other way around, but understand what information you can get out. Are you reading the voltage on a photodiode? Are you looking at actual images of atoms and trying to figure out what's going where? What are you getting out of your system? How do you quantify what good and what bad is? Are you trying to minimize a temperature? Are you trying to maximize a speed? What are you trying to do? And then finally, there we go. What algorithm will you use? Is it going to be global, local? If it's local, how are you going to take your derivatives? And really, the crux is, what can you make use of that will simplify your problem? What do you know about the physics of your problem? What are the relevant frequency scales? What are the relevant time scales? What are the energy levels of the system that you're trying to control? What physics can you make use of? And this is really, I talk about this being a sort of what not to do in quantum control. When we go on to this case study, which we're going to do now, I'm going to tell you a bit about what I did, but I'm going to focus on what I got wrong, because I could have saved myself a lot of time. So I built what we call a shaken lattice atom interferometry. My PhD thesis was 3 words: shaken lattice interferometry, right? And what we basically did was, okay, you know what quantum sensing is, right? We build things, they're very, very nice. Okay, good. Now, if we have a traditional interferometer, well, okay, if you don't know what quantum sensing is, come talk to me. Right, traditional interferometer, lovely glowing source. I had a period in time when I made things out of PowerPoint that I wanted to put effects on everything, and current me is paying the price. I've got a source, I've got 2 beam splitters, got 2 mirrors. The source comes, hits beam splitter. We then have splitting, atom optics, right? So this is real optics. We split the light, it propagates. We reflect it, it reverse propagates. We recombine it on the beam splitter. And then what the output gets put onto 2 detectors, these lovely black boxes that definitely are not the black boxes that you get sold by Thorlabs when you order a photodiode. Yes, they absolutely are. And if you align things right and you've got a lovely red helium neon laser, you get fringes. Yay, fringes. Cool. If you've never built an interferometer in your life, I recommend it. They're pretty fun. Cool. An atom interferometer, and actually this is exactly what we were talking about. Atom interferometers are nice, right? Because they can be more sensitive. If I replace my laser light with an atom, which is slightly deranged, I like my deranged atoms, and we consider the Sagnac effect, and we've got an enclosed area with, all else being equal with light and atoms, where we've got area is length times width, and we've got a rotation rate, which I'll call big omega. Then actually our delta phi that we pick up as we run our waves, be they matter waves or light waves through our system, our delta phi that we pick up will take this form: proportional to the rotation rate in the area, inversely proportional to the wavelength of our waves and its speed. Now, light travels at the speed of itself. Atoms have a de Broglie wavelength for a given mass. And actually, if you take this delta phase, you take the delta phi for the atoms and the delta phi for the light, you get something like 11 orders of magnitude. Exactly. Now, there are elephants in the room. One being, good luck putting your atoms around like the kilometers of fiber that they put in the fiber optic gyroscopes that you find in most jet planes. But this 11 orders of magnitude is enough to get people interested in it. And, that's what we tell the funding agencies. And the funding agencies give us money and we build cool stuff. And now, atom interferometry has evolved from, something that we did in dark, cold laboratories to something that we do in dark, cold laboratories that have like 100-meter towers. And we're measuring fundamental constants and stuff like that. And some people's dark, cold laboratories are like satellites in space, which is cool. So, all right. Now, I'm not going to go through this. This is very much another set of, the band structure and whatnot. But what we actually ended up doing in Boulder, and this is an idea that Dana had, and that I just sort of took and ran with, is that you trap your atoms in an optical lattice potential, right? There's our lattice. This is why I was giving you this background, right? There's our lattice, and here's my control parameter. And you see that it's not multiplying my V sub naught like amplitude modulation would, but this is phase modulation. This is the term that I control. And we use this shaking to control the momentum state of the atoms. We're working in the block band picture. This is a shallow lattice, atoms, as broken eggs in an egg carton. And so what we're controlling are the momentum states. Literally, I'm sitting there and I'm looking at, how many atoms do I have in 0 h bar k, how many in -2, +2, -4, +4, et cetera, et cetera. Good. And so they look something like this. And these are the momentum delta function diagrams that I was showing you. You see there's band 0 and there's band 1. Wow, band 1 sure does look a lot like a beam splitter. Maybe if I'd thought about that 3 years, before I actually realized it when I was doing this optimization, I would realize that actually a beam splitter might be going from band 0 to band 1. Yes, I'll get into that in more detail. So starting with atoms in the ground state of the lattice potential, here, my blue atoms and my red potential, I implement a beam splitter. Half of the atoms are moving this way with some momentum, half of the atoms are moving this way with some momentum. We then just let them propagate. And then we run everything back in reverse. We reflect them, reverse propagate them, and indeed then they recombine back into the ground state. All right, that's good. That's kind of boring, but that's good. What happens is that if we start to accelerate this potential, either via a magnetic field gradient, which is how I did it in Boulder, or by actually accelerating it, which was something that I really, really didn't want to do because that sounded very violent and I wasn't sure my experiment would survive, but eventually we will, then actually we wouldn't recombine back into the ground state. We would recombine into a different state, and by looking at how that state changed, we were able to back out a signal. So how did we optimize the system? Because actually, solving this analytically can only really be done in the simplest of cases. And I was sitting there and I was Googling various papers and I was getting things like quantum chaos. And I was like, oh God, no. So what I wanted though, is I just wanted to go from, I wanted to go back a little bit. Here, I wanted to go from this state to something that had equal population here and equal population here in the ±2 momentum state. And again, it looks a lot like this. Think about the physics of your problem. This is the thing that I didn't do right in my PhD. I didn't think hard enough about the physics of my problem. It took me 2 or 3 years to make this connection. I'd been doing calculations of various bands and whatnot for 2 or 3 years at this point. I had an experiment that worked. It was putting out, I could phase modulate, I could shake my lattice, and I would get all these lovely discrete momentum states. I knew I was going to graduate with the PhD. And then one day I made this connection and I was just like, why didn't I do this earlier? So I'll talk a bit about that. But how did we optimize it in the first case? And the thing is that this is one of the traps that you can fall into with optimal control, because it'll just give you an answer. And you can choose to go try to find the underlying physics, or you can just ignore it. But we started with an initial state and an objective function. And we said, listen, we want to make a beam splitter. Let's shake this system and what comes out, and let's try to change it so that it shakes the system. We optimized a set of shaking frequencies. Basically, we decomposed our phi of t in terms of just a Fourier series. And so we'll start with atoms in an optical lattice. And my computer basically said, oh yeah, I want a split state, right? Half the atoms moving one way, half the atoms moving the other way. Thinks up some phi of t, we modulate the lattice, and we get something that's not this and this are not the same, right? And so it says, no, great. So it goes away, it thinks about it a little bit. Computer thinks about it, the student doesn't think about it. That's the critical bit. And it shakes, and we get what we want. And it's happy. Everybody's happy, right? But what we didn't quite understand was why. And, once the shaking function was known, it was fixed. We could make our entire atom interferometer. We could split the atoms apart. We could bring them back together. They recombined into the ground state. I added an acceleration signal. We saw how this changed. We took a bunch of data. We published it, and it was really cool. And I got a PhD, right? But I didn't think about this system in the right way. I knew this. I knew my state transfer problem. I knew what my controls were. I knew what their limits were because I was building the experiment. I knew what information I could get out of my system. I couldn't get phase information out. I was quite literally taking pictures of the atoms and counting how many were in this blob over here versus how many were in this blob over here, and then taking how many were in the center blob and on the side blobs. And I was, I basically was a professional blob counter, right? And so I knew what I could measure, and I knew that phase wasn't one of these things. So while I still thought about phase, I could only think about phase in terms of computation, which I was doing computation, but also what I really cared about was the experiment. I knew what algorithm I was going to use. I've used a genetic algorithm. I've used a gradient-based algorithm known as the Krotov method. I used a Nelder-Mead-based algorithm, which is sort of a global optimizer. That was based on something called the Crab algorithm. I have great love for the Crab algorithm. Ask me about the Crab algorithm. I might even have some time to talk a bit about it, but that's not, we won't get into it today. Good. So I knew all of this, but this was what I didn't think about until I was like 3 years in. And it had its upsides and its downsides. The upside was that when I started thinking about it, I was able to publish a paper that was like, look, we thought about this and more physics came out. But like, really, we should have, again, we did this in the wrong direction. So how could I be smarter about optimization? So our initial simulations and our experiments basically broke our control down into the sum of Fourier components. And I usually picked about 5 random frequencies, and I picked them within 100 kilohertz bandwidth because that's more or less what I could do in the experiment, right? So I just picked something out. And it's actually quite lucky that I picked it within the bandwidth that I picked it because I just didn't think about the physics of the problem. Like I said, the split states look like higher order block states, higher band block states. Everything that I'm talking about, I worked at 0 quasi-momentum because we assumed we loaded the atoms into the lattice at 0 quasi-momentum. But these split states look like block states. There's the 0th band, the first band. Okay, that looks like a beam splitter with 2 h bar k. Second band doesn't quite look like a beam splitter with 2 h bar k, but we could try. Third band, that's a 4 h bar k splitter. Fourth band is too. And actually the difference between band 3 and band 4 is that there's a pi phase difference between one of them. So band 3 is, they have the same phase. Band 4, one has a flipped phase. This is also interesting from an atom interferometry point of view. Didn't think about these things. Band 5, now we've got a 6 h bar k splitter. 6, another one, right? Same phase flip thing that I was talking about. 7 is 8 h bar k. This is awesome. They're really straightforward ways to get these gains in sensitivity that you get from doing high momentum transfer. Yeah, okay, this isn't 100 h bar k, but I know ways to do that too. And I can't do 100 h bar k if I can't start with 6. Right, so this high momentum transfer, all of a sudden this was making sense. I'm sitting here and I'm looking at this 3 years after I started, right? It's a good thing the US PhD was long, right? I needed some of that time, right? My students come to me and they're like, how did you do so many things in your PhD? I was like, I had twice the amount of time you did. So yeah, for better or for worse. So then the idea was, well, let's just ignore these random frequencies and let's start driving these band-to-band transitions using phase modulation. And you can drive these sort of single or 2 photon transitions between states of opposite or same parity, right? So I talked a bit about parity yesterday. Band 0 has even parity, 2, 4, 6 all do, 1, 3, 5, 7 all have odd parity. And one of the nice things about phase modulation versus amplitude modulation is that if I sit there and I modulate the amplitude of my lattice, I can only make transitions between states of the same parity. and I can, dig that math out for you and do it all. And, I lived and died this stuff for like 3 years. But with phase modulation, you can actually do both. There's nothing telling you that you can't make a single photon transition between 0 and 1 or 0 and 3, 0 and 5. And then it's typically a 2 photon. Okay, photon is a strong word. It's a phonon. These are not photon transitions. These are in like the kilohertz regime. Again, very lucky that I did this with the kilohertz. So you can drive these types of transitions. Come on, you can do it. Did it just die on me? Oh, there we go. Okay, cool. So yeah, basically our matrix elements to drive these even and odd band transitions looked like, initial band, final band, and either the sine or the cosine of what we were trying to do. And the reason why you get the sine and the cosine is because you're doing that phase modulation. Part of what made this such a complex system is what made it so versatile. And we could actually just really easily, once I figured this out, I sat down and I did the experiment. And I was able to get splitting with an error with a fidelity as good or better than what I'd done previously. My fidelity was limited to my error was limited to about 10% because our imaging wasn't that great. Subsequent people working in Dana's lab fixed that, and now their pictures look beautiful. Mine didn't. How it got into PRL is beyond me. I think I just looked kind of desperate. And so what you could see is that the transition between the first and the second band, I didn't know precisely what my lattice depth was. Again, something that I learned how to fix and that future groups did, but I was the first one to build a lattice in Dana's lab, and I didn't know what I was doing. But I knew that the 0 to 1 transition lay somewhere between 21.5 and 22 kilohertz. That was basically the transition to go from here to here. That energy was about 20-something kilohertz. So I did a scan of my frequencies, and I did a scan of my amplitude, because basically I fixed my time and I scanned my amplitude. I could have fixed my amplitude and scanned my time. I just picked one, and I got splitting as good as I'd gotten with all of this complex, randomly guessing my frequencies. And it just worked. And so this was a single phonon transition. And then I tried to do the two phonon transition. And so indeed, the transition between 0 and 2 was at about 30-something kilohertz. Half of 30-something is 17. And indeed, I was able to split from band 0 into band 1 and band 0 into band 2. And I got these really, really nice results. And that was cool. All of a sudden, this was working. I think we were able to demonstrate 4H bar K experimentally, but then the system had this like slow vacuum leak, and it just stopped really working all that well. So this was kind of my last hurrah as an experimentalist because of that leak, at least in Boulder. Okay, cool. Are you gonna function? Yes, there we go. Goes very quickly. So then we decided, okay, let's actually look at this improved optimization. And I just limited my optimization to these band-to-band transitions. And I was able to learn this much more quickly. With optimization, with my computer, without all of these issues due to, imaging and whatnot, I was able to optimize very, very quickly. So all I did was I looked at these matrix element overlaps. Oops, wrong way. So these guys here, these matrix elements, all I did was calculate them. And I plotted them here between initial bands and final bands. And this is just a magnitude. And I picked the ones, and it's reflected because it's a matrix going from band 1 to band 0, and band 0 to band 1 is going to have the same amplitude. And I basically picked 1, 2, 3, 4, 5, 6, and then there's like 5 up here. So I was down to 11 frequencies from kind of continuum of infinity. And I just ran the learning algorithm using these guys. And what you see here, this is a genetic algorithm, which is probably one of the least efficient ways to do this. And the black was running with just sort of randomly selecting from all frequencies. And this is an average, and this is a best, the average of like 10 runs with the open circles, and the best of these 10 runs with the closed circles. Same thing here with the red squares, except this is for the select frequencies. And you see the selected frequencies, I optimized to within 1% in one iteration. My guesses are already better. And then 4H bar K was a little bit more difficult, but indeed I could get to within 1% in like 5 iterations. That was something I could do experimentally. You know, doing 100 iterations wasn't something I could do experimentally because my vacuum quality would degrade over time as I sat there and I made BEC after BEC after BEC. And so I'd be able to run this thing for 6 or 8 hours if I was just really, really nice to it. And then I have to like turn it off and give it a break. I did 6H bar K. And indeed, I can get it to within 10 iterations. And this black line up here hasn't even moved. So this is crazy how much better I did once I started thinking about the physics of my problem. And so that's really like, that's why I give this talk, is because like, one, I love optimal control. I think it's really cool. If you have a problem that you think optimal control will help, come talk to me. It's fun. I like to do sort of my optimal control evangelism. A lot of people, increasingly people are thinking about it. I'm not original in this. I'm not claiming to be original in this. But the thing that I can tell you, and the thing that is best to tell, you know, PhD students is that, and postdocs and whatnot, professors, is think about the physics of your system. You will do so much better if you think about the physics of your system. Basically, we were avoiding what we call the curse of high dimensionality. If I'm trying to select 5 random frequencies, then my optimization landscape might be 5-dimensional, but it's going to change dramatically based on what frequencies I pick. Actually, then if I simplified things to an 11-dimensional space, which might have been higher, you know, in terms of optimization, but I knew those 11 dimensions actually worked for my problem, and that I wasn't sitting there shaking with frequencies that didn't help me. And actually, there's been some work out of Emmanuel Bloch's group, and I believe that's when I think Ulrich Schneider's the last author on the paper when he was out there, where they did this. They showed that if you do this phase modulation and you're right on the band-to-band transition, it works really, really nicely. But if you're away from that band-to-band transition, all you're doing is heating up your system. If I've got something that's 100 nanokelvin and I'm shaking it at some completely useless frequency, I'm not just doing nothing, I'm actively hurting myself. And this is actually pretty interesting from a physics point of view, because if we want to implement our beam splitters as quickly as possible, we know what frequency we need to shake at, but we have to turn the system on and off, and that's going to introduce some higher frequency components. And so there are kind of fundamental limits that I'm increasingly trying to get at in terms of how fast you can do things before you really just make them hot instead. So yeah, we did a lot better once we started thinking about the problem. So, all right, what's the point? Everybody should play with atoms. There's a few people that play with neutrons. They can continue playing with neutrons because that's pretty awesome. But atoms are fun. And the luckiest of us can actually just have a really good theory model. A lot of the work that Jörg Schmiedmeyer's done in collaboration with folks like Tommaso Calarco and the folks that, you know, really made the Crab algorithm, and I think also Misha Lukin's group, and I think Jelesko, who does ions, you know, they've worked together and they get these, you know, they model their system really, really well, and they get really, really nice theory models, and indeed the experiment agrees. If you can do that, that is awesome. And that's really what I strive for. It didn't work when I was in Boulder. It now works in Boulder because they have a better model of their system, because they understand better what's going on. And likewise in Bristol, the system that we're trying to build, we're trying to build in that intrinsic understanding of what we're actually trying to do. So if you've got a good model, then you can optimize things computationally, plug that optimization into the experiment, and if you get close, then you can do some, you know, in experiment closed loop control. But if you're really, really good, then it just works, and that's awesome. Optimal control methods are very versatile, and they depend on what you're trying to do. Is it expensive to take derivatives? Is it not? Right? What are the limits of your system? How are you trying to do this? But, you know, that's really what you want to do. Avoid the curse. Don't be cursed. PhDs are long and hard enough. Don't make your life harder. Postdocs are, you know, long-ish and hard and stressful enough, right? Think about the physics that you can apply to the problem. Definitely do that. If you don't do that, then, you know, that's no fun. And that's really all I've got. You know, I only have 5 minutes, so there's, you know, what I think I'm going to do tomorrow is I'll walk you through quickly a couple of algorithms so you get an idea for what this looks like. And then we'll talk a little bit about what it means to make a control robust. And that is a control that does what you want even when the things that you don't want happen. Like your laser powers fluctuate, your lattice depths fluctuate, the temperature in your lab fluctuates, you know, all of these things. So that's what I have for you. Thank you so much. Any questions? We've got some time. Yes.
The lambda I.
Yep.
Said like you shouldn't pick them by random, but the best that you can do is an educated guess.
If I said yeah, typically, yeah. What you want to do, and there's even like a whole bunch of people that, let me go to the place where you can actually see what's going on in case you happen to be sleeping a little bit through that, which I get. There we go. Are you going to share? Are you going to function? Yes, there we go. Very good. Okay, so there's my ever important functional. There's all the words that were on that slide. So this is really similar to like hyperparameter optimization when people do like machine learning and neural nets and that sort of thing. And often what I'd say you should do is start with an educated guess. That said, I've often had functionals where I have 2 or 3 terms, and I will literally just do a sweep. I'll set one of my lambdas to be constant, and I'll vary the other lambda with respect to that one. And then I'll just see what works the best, where I get the best solutions. So like you can optimize you can optimize the parameters that you use to optimize your system. That said, I will typically, with a system like this, my lambda naught will be far and away my most important parameter. Because all else being equal, if I don't have a high fidelity, I just don't care. But based on what I want, and oftentimes I don't have a parameter like this, but I will often have a parameter like this, because this is one of the best ways to just shoehorn in a bandwidth limitation. And so usually what you can do is as you vary then this lambda b, you'll get higher and lower bandwidth solutions. And so I would say that it is an informed guess. But if it's, of course, the first time you've made a guess like this, I would say, you know, emphasize your fidelity, but it's worth exploring the effect that these other terms have. I know that that's not at all like a very, like it's a very waffly way to put it, but does that make sense? No, and different problems are going to have different constraints, and you're going to have different functionals. Yeah, this is, yeah, and you get better at it with time. It's also worth going and reading some of the papers that do this type of thing in systems that are similar to what you do. Look at their functionals. You will find some where you're like, my God, what were you thinking? That's all right, don't use those. But a lot of them will make a good bit of sense, and you can kind of see how people weight different terms. There's a really nice PhD thesis that was written by somebody in the group I did my postdoc in. And so if you're really curious, like he goes into the nitty gritty, and I can send you a copy of the thesis. It's publicly available, so I don't really feel that bad about it. This guy was named Jesper Jensen, if you say it American style. Yeah, we're on a couple, I think we're on one paper together, so you can find his name and then you can find his thesis. But it's a really, his first chapter of his thesis is a really nice introduction to these types of things. Yeah, any more? Yeah, it was a long night last night, wasn't it? It was a good night. Yeah.
It's just about going back to the other, like the last time when you were speaking about if you go to a deep lattice, you start having like this blurry momentum.
Mhm.
Can you
is it correct to think about that just in terms of you have wave packets? If you kill the coherence between all of them, you're gonna have like random interference between all of them.
Yeah, that's exactly what happens. And actually, the first papers that showed these like superfluid to mod insulator transitions, one of the more interesting things that they showed is that as they ramped up the lattice step, they went from something that had coherence, right? The atoms were clearly talking to each other because they were interfering and getting these nice momentum states, to something that clearly wasn't, because you were effectively taking the Fourier transform of a bunch of delta functions, which gives you a lovely blob. And then what they found is they could ramp up, and then they could ramp back down, and they restored the coherence. And this was like fundamentally a really cool physical thing that they could do. So yeah, cool. Wolf, I think you had a question.
Question. So just about what you just said now, by the way, so coherence is always a different, dangerous word, right?
Mhm.
Because obviously the state that didn't interfere and give just a block still had tremendous coherence, but in real space and other space,
Mhm.
in non-phase space, in phase.
Mhm.
But just more back. So our next topic, which is given by Yannick, on the again on AI, and actually these two things talk very.
I think they do
very-
talk very
in a way,
nicely to
very
each other.
lucky that we reordered our lectures, because in a way many of these things map onto AI as well. Because AI in some way is also an optimization, as in machine learning, as we've seen in the first lecture, is also an optimization process, and can be mapped to, well, many of the things said now apply directly to these sort of
Yeah.
things.
Yep.
And you touched about the single value, that in order to optimize, you have to have one single value that see that it's good or not. And that's actually something quite interesting, because people get upset or get surprised by it, or even upset by that in real life. But it is something fundamental. Whenever a decision needs to be taken, it can only be based in the end on a single value. And an example where you've heard that before, where you yourself might have been upset about that, is airplanes. So on airplanes, you have the fact that if the companies say your life is worth 1 million euros. If you die, bad luck, it's 1 million euros. It's nothing else. And people get really, really upset about that, because how can you put money into a life? But if you build the machine, the turbine, or if you buy a ticket, that costs money. So you have, it's two completely orthogonal coordinates, and then you have to put your lambdas in the front of it to decide whether the blade is made of gold or titanium or crappy aluminum, or the cheap aluminum from there, or the pretty aluminum somewhere else. And that lambda has units, because it has to transfer one quantity. You've written down anything unitless, but one quantity or another. And that's always true. So it's a very, very general thing, but it's for machine learning.
You don't have to screw these numbers as well, so he went right now.
Yeah, you should really do it right, because maybe you managed to get your promotion then, but the next CEO has to have a lot of explaining, or the next engineer has to do a lot of explaining.
Yep.
So anyway, so the single value thing is not doesn't come from physics, it doesn't come from AI, it's life. Good.
Yeah.
Coffee.
Coffee.
And again, I'm not in toilets. Sorry, I'm not working well. The device layer has been alerted. Carrie, you shared your presented screen and not the screen. We'll have to remount your slides if you will manage.
Okay, I'll send the slides, and I'm happy to help with that. The presenter screen I don't think was particularly interesting. I don't typically put notes on my slides, but yeah.
Easy to cut.
Yep.
But you also managed to get a little warning box on your presenter screen, which you can get away.
Oh, cool.
Hiding part.
Oh, cool. Yeah, sorry about that. Oh, yeah, absolutely. I did realize I would have a tendency to round over here, and so I tried really hard not to do that.
Okay, thank you.
I have two questions.